Good morning, everybody. So, in this lecture 4, we will discuss on the derivation of continuity equation for one-dimensional flow. When we talk about continuity equation in one-dimensional flow, that means the flow is in the form of streamlines. So, straight away, I will take you to the derivation aspect. So, today's lecture is mainly focused on the derivation of the continuity equation applicable to one-dimensional flow. In the previous class, if you recollect, for three-dimensional flow, we have derived the continuity equation for steady incompressible fluid flow as dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. For 2D flow, we are dou u by dou x plus dou v by dou y is equal to 0. Now for one-dimensional flow, if you write it is dou u by dou x is equal to 0, which really does not signify any meaning, and it is not really taking into account the area of cross section, which is very, very important actually in the study. So that's why now when we want to derive the continuity equation applicable to one-dimensional flow, first we will take actually consider a tube-shaped parallelopipe along a stream tube of length delta S. Suppose now I will draw the figure. So if this you consider it as a stream tube of length delta S. So this is bounded by the streamlines. So this one, inner one, is what we call it as the stream tube. So if I call this as Mn and this as M dash N dash. Now you all know that in the case of stream tube, the flow is tangential to the stream tube and there is no flow across the stream tube. So kindly remember that the entire flow is in the tangential direction. Now, these are all basically, if you take it, these are all the streamlines. Now, what I'm taking is, like in the previous section, I take P is the central point of this stream tube. So if I take this, so this is how it is. So now at P, if I take the along the tangential direction, first what is the mass at P I need to find out. Like same in the case of what we have done in the Cartesian coordinates. So if I find what is the mass of fluid flowing through the center of the stream tube at P, if I calculate, then naturally I can calculate the mass of fluid entering through Mn and mass of fluid leaving through M dash and N dash, and then finally I can clearly derive the equation. Now if I take it, if at central section, if at the central section of the elementary stream tube, A is the cross sectional area, V is the mean velocity of flow, rho is the mass density of the fluid, then mass of fluid passing passing through the section at the point P. If I take it, A is the area of cross section multiplied by the velocity, that is the volume of fluid flowing per second at the center, then mass if we want multiplied by rho, so it is equal to rho AV at the center actually. Now, what we are not interested more at the center. By determining at the center, we want to now kind of find out what is the mass of fluid entering through Mn and what is the mass of fluid leaving through M dash N dash. So if I calculate that mass of fluid entering through Mn per second is equal to rho AV, because already I am putting straight away minus because it is on the left hand side, dou by dou s of rho AV into at what distance it is there, delta s by 2. Dou by dou s of rho AV represents that change of mass per unit distance, but the distance is delta s by 2. That is why we have written like that. Similarly, mass of fluid leaving through M dash N dash per second is equal to rho AV plus dou by dou S of rho AV into delta S by 2. Therefore, the difference of mass entering and mass leaving is equal to rho AV minus dou by dou S of rho AV into delta S by 2 minus rho AV minus dou by dou S of rho AV into delta S by 2. So rho AV gets cancelled. So it is minus 2 into dou by dou S of rho AV into delta S by 2. This 2 and 2 cancels. Finally, it is equal to minus dou by dou S of rho AV into delta S. So this is equation 1. Now, rate of increase of fluid mass rate of increase of fluid mass is equal to this we have to calculate. So first thing for that I have to calculate next first volume of the fluid in the in the what you call it as in the stream tube is equal to volume is equal to area into length is delta s. Then mass is equal to that is rho into A into delta S. Then basically rate of increase of fluid mass is equal to dou by dou T of rho A into delta S. Call this equation 2. So according to continuity equation, according to continuity equation, net mass of fluid net mass of fluid that has remained in parallel pipe, which is nothing but the difference of mass entering per second, mass leaving per second is equal to rate of increase of fluid mass in the parallel pipe. Therefore, the first one is minus dou by dou s of rho AV into delta S by 2. This is the difference, which is equal to dou by dou T of rho A into delta S. If I bring this onto the other side, dou by dou T of rho A into delta S plus dou by dou S of rho AV into delta S by 2. This is the most general equation for one-dimensional flow. In case of steady flow, in case of steady flow, dou by dou T of rho A into delta S is equal to 0. Therefore, dou by dou S of rho AV into delta S is equal to 0. As delta S cannot be 0, it will be dou by dou S of rho AV is equal to 0. This is the equation of continuity for one-dimensional flow. Rho AB is equal to constant. O1, A1, V1 is equal to rho 2, A2, V2. If the fluid is same, then rho 1 is equal to rho 2. Therefore, A1 V1 is equal to A2 V2. This is the general equation we use as continuity for solving the pipe flow problems. So this A1 V1 is equal to A2 V2. AV represents the volume of fluid flowing through any section per second, and is also called as rate of flow. Rate of flow. And rate of flow is also called as discharge. So what is finally the discharge? Discharge is nothing but actually rate of flow. Rate of flow means volume of fluid flowing through any section per unit time per second. So discharge is represented by Q. Q is equal to AV, and continuity equation is Q is equal to A1 V1 is equal to A2 V2. This is the generally which we apply in any of the problem solving cases. So if I want actually the velocity at any point, I can use velocity is equal to Q by V. Velocity V1 is equal to Q by A1. In any problems, if the discharge and diameter of the pipe is given, then diameter of the pipe is known means area of cross section is known. So if discharge is given, then you can find out velocity. If velocity is given, you can find out discharge, which is commonly being followed. Our velocity V2 is equal to Q by A2. So this continuity equation, why we have derived for the one-dimensional flow is it is finally accounts to rho A1 V1 is equal to rho A2 V2, and finally A1 V1 is equal to A2 V2. And this application is very much useful that AV is nothing but actually the discharge. Discharge, you should remember, discharge is equal to area multiplied by velocity. What is the definition of discharge? The definition of discharge is equal to it is volume of water flowing through any section of a pipe per unit time, that is per second. So this is what we require actually in many of the problems in fluid mechanics. Discharge is equal to area multiplied by velocity, and this is the equation we will use. And if suppose we want to really at two sections, if we are comparing it, discharge remains constant. A1 V1 is equal to A2 V2. What that A1 V1 is equal to A2 V2 signifies, it is the continuity equation for the one-dimensional flow. So this if you remember, and here I will stop, and in the next class we will go into the another section. Thank you very much.
Like, share, and subscribe. Hit the bell icon for more updates.